After about age 20, we may have all the insulin-producing beta cells we're ever going to have in our pancreas, and so if we lose them, we may lose them for good. Autopsy studies show that by the time type 2 diabetes is diagnosed, we may have already killed off half of our beta cells. You can do it right in a petri dish. Expose human beta cells to fat, they suck it up, and then start dying off. A chronic increase in blood fat levels is harmful, as shown by the important effects in pancreatic beta cell lipotoxicity. Fat breakdown products can interfere with the function of these cells and ultimately lead to their death. And not just any fat, saturated fat. The predominant fat in olives, nuts, and avocados gives you a tiny bump in death protein 5, but saturated fat really ramps up this contributor to beta cell death. Saturated fats are harmful to beta cells, harmful to the insulin-producing cells in our pancreas, cholesterol too. The uptake of bad cholesterol, LDL, can cause beta cell death as a result of free radical formation. So, diets rich in saturated fats not only cause obesity and insulin resistance, but the increased levels of circulating free fats in the blood, called NEFAs, non-esterified fatty acids, causes beta cell death, and may thus contribute to progressive beta cell loss in type 2 diabetes. And this isn't just based on test tube studies. If you infuse fat into people's bloodstream, you can directly impair pancreatic beta cell function, and the same when we ingest it. Type 2 diabetes is characterized by defects in both insulin secretion and insulin action, and saturated fat appears to impair both. Researchers showed saturated fat ingestion reduces insulin sensitivity within hours, but these were non-diabetics, so their pancreas should have been able to boost insulin secretion to match, but insulin secretion failed to compensate for insulin resistance in subjects who ingested the saturated fat, and this implies the saturated fat impaired beta cell function as well, again just within hours after going into our mouth. So, increased consumption of saturated fats has a powerful short and long-term effect on insulin action, contributing to the dysfunction and death of pancreatic beta cells in diabetes. And saturated fat isn't just toxic to the pancreas. The fats found predominantly in meat and dairy, chicken and cheese are the two main sources in the American diet, are almost universally toxic, whereas the fats found in olive, nuts, and avocados are not. Saturated fat has been found to be particularly toxic to liver cells in the formation of fatty liver disease. You expose human liver cells to plant fat, and nothing happens. Expose liver cells to animal fat, and a third of them die. This may explain why higher intakes of saturated fat and cholesterol are associated with non-alcoholic fatty liver disease. By cutting down on saturated fat consumption, we may be able to help interrupt this process. Decreasing saturated fat intake may help bring down the need for all that excess insulin. So either being fat or eating saturated fat can both cause that excess insulin in the blood. The effect of reducing dietary saturated fat intake on insulin levels is substantial, regardless of how much belly fat we have. And it's not just that by eating fat we may be more likely to store it as fat. Saturated fats, independently of any role they have of making us fat, may contribute to the development of insulin resistance and all its clinical consequences. After controlling for weight and alcohol and smoking and exercise and family history, diabetes incidence was significantly associated with the proportion of saturated fat in our blood. So what causes diabetes? The consumption of too many calories rich in saturated fats. Now, just like everyone who smokes doesn't develop lung cancer, everyone that eats a lot of saturated fat doesn't develop diabetes. There's a genetic component. But just like smoking can be said to cause lung cancer, high-calorie diets rich in saturated fats is currently considered the cause of type 2 diabetes.
Type 2 diabetes, also known as adult-onset diabetes, is a metabolic disorder characterized by high blood glucose. Obesity is thought to be the primary cause of type 2 diabetes in people who are genetically predisposed. Thus, overweight people have increased levels of glucose circulating in their blood. The pancreas is an organ which produces hormones that control blood glucose levels. The hormones that control blood glucose are produced by clusters of cells in the pancreas called islets. Here glucose is shown arriving at the islets via the bloodstream. The glucose is taken up by cells in the islet called beta cells. The beta cells respond by producing the hormone insulin, which lowers blood glucose. In type 2 diabetes, high levels of glucose stimulate the beta cells to produce lots of insulin to lower the blood glucose levels. The insulin is taken up by the blood vessels for transport to muscle, liver, and fat, where it allows those tissues to absorb glucose. Unfortunately, sustained production of insulin also leads to secretion of large amounts of another hormone-like substance by the beta cells. White blood cells, which live in the islet, respond to this hormone and consume it. We are now inside an islet white blood cell at a magnification of 250,000 times. The hormone, in combination with high glucose, causes production of free radicals inside the white cell. The free radicals activate a sentinel protein that originally evolved to protect us from microbial infection, causing it to unwind. The newly active sentinel proteins then aggregate with 6 other proteins to form a ring. Seven adapter proteins then bind to the ring. The adapter proteins work to capture specialised inactive proteins from the surrounding cell fluid, bringing 2 halves together to form the active whole, which is then released. This entire structure is called the inflammasome, and its sole purpose is to act as a platform for combining and activating these proteins. The newly active proteins then convert yet another small signalling protein, splitting it into its active form. This protein is the key protein involved in inflammation in the body. The inflammatory protein is then secreted from the white blood cells into the islet. Unfortunately, this inflammatory protein causes death of the beta cells. Over time, beta cell death causes the islets to shrink, accelerating disease progression. As the islets are now greatly reduced in size, they cannot produce enough insulin to control blood glucose levels. Over time, high blood glucose causes damage to many different tissues throughout the body. What originally evolved as a defence mechanism against infection now seems to be a driving force for inflammation in type 2 diabetes. Chronic diseases associated with inflammation are the most common diseases of ageing in the Western world and represent our greatest health threats in the 21st century. Australia is facing an increasing epidemic of type 2 diabetes. There are now approximately 1 million people living with diabetes and around 100,000 new diagnoses each year. Obesity is thought to be the primary cause of type 2 diabetes in people who are genetically predisposed. In part 1, we explained how inflammation in type 2 diabetes destroys the pancreas tissue and dramatically decreases insulin production. Here we describe the insulin receptor in type 2 diabetes.
What we have discovered is the molecular detail of how the hormone insulin binds to its so-called receptor protein on the surface of a cell and instructs that cell to take up glucose from the blood and to store it as an energy source. The receptor itself actually spans the cell membrane, so it has a part outside, a part inside, and insulin binds to the part that is outside. Insulin is a small molecule whose structure was determined a long time ago in 1969. But it's been unknown how it interacts with the receptor, and that is what we have discovered. And its interaction I've characterized as a molecular handshake as the two proteins dock together. When insulin binds to the outside parts of the receptor, it brings the two halves of the receptor together, and at the same time, the two parts inside of the cell unwind and make contact. These two proteins then activate each other.
This activation allows the insulin signal to enter the cell. Specialised proteins interact with the activated receptor just below the cell's surface. The receptor activates these proteins, and they in turn are able to activate multiple other proteins in a long signal cascade. This complex signalling process eventually tells the cell to take up glucose for use as an energy source. The long signal cascade allows tight control of the signalling process, as it can be turned on or off at many different points along the way. In type 2 diabetes, we believe insulin binds to its receptor normally, but the signal is not sent into the cell and the signal cascade does not develop. This is known as insulin resistance. This means that glucose cannot enter the cell and blood glucose remains high. Over time, high glucose levels damage many different organs.
Insulin, as you know, has been used to treat diabetes for a very long time. But all of those formulations and types of insulin that have been used in the diabetes context have been designed and formulated without any knowledge of the way in which insulin actually interacts with the receptor. And now for the first time we've got a picture of that, and we can use that into the design of new insulins that could be used for the treatment of diabetes. So we could imagine, for example, the design of insulins that act for a longer period of time, design of insulins that act more quickly, design of insulins that are more stable upon storage, and that's where we'd like to go with our discovery.
Drug companies are hoping to capitalize on the fact that the consumption of certain plants appears to lower the risk of diabetes by isolating the active components for use and sale as pharmacological agents. Though not as profitable, why not just eat the plants? One plant in particular that's now been tested is flax. We've known for 20 years that having ground flax seeds in your stomach can blunt the blood sugar spike from a meal, but it's never been tested in diabetics until now. An open-label study on the effect of flaxseed powder supplementation in the management of diabetes. A tablespoon of ground flax seeds every day for a month, and, compared to the control group, a significant drop in fasting blood sugars, triglycerides, and cholesterol, as well as the most important thing, a drop in A1C level. This was just after a month. Though if one's sugars are already well controlled, though there may be no additional benefit. No weight gain was reported in people adding a quarter cup of ground flax a day to their diets for 3 months. In fact, the flax group ended up with a slimmer waist than the flaxseed oil or control group. Even up to nearly a half cup a day, more than I'd recommend, still no significant weight gain, though this was only after a month. How does flax help control diabetes? Well, flaxseed consumption may improve insulin sensitivity in people with glucose intolerance. After 12 weeks of flax, there was a small but significant drop in insulin resistance, perhaps related to the drop in oxidant stress, given the antioxidant qualities of flaxseed phytonutrients. Now, this was a small, unblinded study. It's hard to come up with a convincing fake flaxseed placebo. So look, if this was some drug they were testing, I'd never prescribe it based on this one study, but it isn't a drug, it's just flax seeds. There's just good side effects. So even if this study was a fluke or fraud, flax seeds have other benefits. So even in the worst-case scenario, I'd still end up benefiting my patients, not quite ready or able to reverse their diabetes completely with a completely plant-based diet. In the past 2 years, 6 separate meta-analyses have been published on the relationship between fish consumption and type 2 diabetes. The whole point of a meta-analysis, though, is to compile together the best studies done to date and see what the overall balance of evidence shows. The fact that there are 6 different ones published recently highlights how open the question remains. One thread of consistency, though, was that fish consumers in the United States tend to be at greater risk for diabetes. If you include Europe too, then fish eaters appeared to have a 38% increased risk of diabetes. On a per-serving basis, that comes out to be about 5% increase in risk for every serving of fish one has per week. To put that into perspective, a serving of red meat is associated with a 19% increase in risk, but that's per day. Just one serving of fish a week is 5%, so a serving a day would be like a 35% increase in risk, worse than red meat. But why? Well, fish intake and omega-3 fats may increase type 2 diabetes risk by increasing blood sugar levels, as found in a review of the evidence commissioned by the U.S. government. An increase in blood sugars in diabetics given fish oil. Or maybe because the omega-3s cause oxidative stress. A recent study found that the insulin-producing cells in the pancreas don't appear to work as well in people who eat 2 or more servings of fish a week. Or it may be because of the environmental contaminants that build up in fish. It all started with Agent Orange. We sprayed 20 million gallons of this stuff on Vietnam, and some of it was contaminated with trace amounts of dioxins. Though the Red Cross there estimates 1 million Vietnamese were adversely affected, what about all the servicemen, the U.S. servicemen who were exposed, spraying it across the countryside? Reports started showing up that veterans exposed to Agent Orange appeared to have higher diabetes rates than unexposed veterans, a link that's now officially recognized. These so-called persistent organic pollutants are mainly man-made industrial chemicals, and among the most hazardous compounds ever synthesized. They include dioxins, PCBs, certain chlorine-containing pesticides, all of which are highly resistant to breaking down in the environment. Initially described for their deleterious effect on reproductive function and their ability to cause cancer, there is now a growing body of evidence showing that exposure to these pollutants leads to metabolic diseases such as diabetes. This is a breakthrough that should require our greatest attention.